Welcome everyone. This is Dr.JaskaranSingh, and in this video lecture, I will be teaching you the concepts of rolling contact bearings. I'm hoping that up till now, you would have covered or studied the design of various machine elements such as shafts, keys, couplings, gear drives, belt drives, and a few others. In this lecture, we will talk about another very important machine element, that is rolling element bearings. So first, we need to understand what are bearings, why do we need them, or where are they used in practical life situations. So this is how a rolling element bearing looks like, or more precisely, this is what we call as an anti-friction bearing or deep groove ball bearing. Now, a bearing is a mechanical element that permits relative motion between two parts, such as the shaft and the housing, with minimum friction. One of the main functions of a bearing is to ensure free rotation of the shaft or the axle with minimum friction. So, rolling element bearings are key mechanical components of any modern world rotating machinery. Or more simply, just think about any power producing or power consuming device around you. So when I say power producing devices, you can think of motors, engines, etc. When I say power consuming devices, you can think of pumps, compressors, etc. So majority of the power producing or power consuming devices have rotational motion associated with them. And whenever you have rotation, you definitely need bearings. So in more practical scenarios, you can find bearings in motors, rear and front wheel of your bicycles, wheels of your motorbikes, cars, etc. And you even have ball bearings in your computers or laptops, hard disk drives. So I hope by now you would have understood what are bearings and where they are used in practical life situations. Now, just to familiarize you all with the basic terminology of bearings, please have a look at this picture. So this is what you would call as the outer ring or outer race of the bearings. This is what you would call as the inner ring or inner race of the bearings. So as a general statement, do remember that in most of the cases, the outer ring is stationary and the inner ring is always rotating. So the inner ring is the place where the shaft resides and it is rotating at the shaft rotational speed. These are what you call as the rolling elements, and in this case, the balls of the bearing. This golden ring is what you call as the cage of the bearing, and its main function is to ensure the precise location of the balls. Now, we need to understand the concept of loads acting on the bearing, and more precisely, the type of loads which can act on the bearings. So when I say the term load, it is defined as the force a bearing must support. So when the equipment is in operation, the load is considered as a dynamic load, and during the idle period, when the machine is stopped, a static load condition exists, solely due to the weight of the component parts of the machine. Now there are two types of load a bearing can withstand: radial loads and thrust loads. Figure 1 here depicts radial loads acting on a shaft. This is the shaft, and this portion is basically the bearing which is supporting the shaft. Figure 2 depicts the thrust load acting on a shaft. Now, radial loads are forces that occur at right angles to the shaft. These forces tend to make the shaft move side to side or up to down. So the thrust loads are forces that are directed axially along the length of the shaft. These forces tend to make the shaft move back and forth along its axis. As a more general depiction, you can have a look here where we have a bearing which is supporting a shaft, and there is a radial force Fr acting in this direction and an axial or a thrust force acting in this direction. Now, Based on the type of loads, there are different types of bearings. So a bearing which can support radial loads is known as a radial bearing, and a bearing which can support thrust loads is known as a thrust bearing. Now, in order to select a proper type of bearing, we will be talking about three different terminologies. One is the static load carrying capacity of a bearing. The second one would be the dynamic load carrying capacity of a bearing. And the third one would be the rated life of a bearing. Now we'll talk about these concepts one by one. So the first topic is static load carrying capacity of a bearing. As I mentioned earlier, a static load is defined as the load acting on the bearing when the shaft is stationary. Now, it produces permanent deformation in the balls and races, which increases with increasing load. Now, the permissible static load therefore depends upon the permissible magnitude of permanent deformation. So, a formal definition of static load carrying capacity would be that the static load carrying capacity of a bearing is defined as the static load which corresponds to a total permanent deformation of balls and races at the most heavily stressed point of contact, equal to 0.0001 of the ball diameter. So this is what you would call as the most heavily stressed point of contact. In order to explain this definition in some simpler terms, let's look at the second definition. So the static load carrying capacity of a bearing is the amount of static load it can withstand before the sum of the ball and raceway deformation equals 0.01% of the ball diameter. Now with this in mind, let's move. One another thing that you need to remember is that the formula to evaluate or calculate the static load carrying capacity, they are given in standard data books for different types of bearings. However, while selecting the bearings, it is not necessary to use these formulas. The reason being, whenever you go to a market to buy some bearings, the value corresponding to the static load carrying capacity is already provided by the manufacturer for that bearing in the manufacturer's catalog. But we need to understand how these formulas are derived. So we'll talk about the derivation now. Now, there is this equation which is known as the Strybak's equation, which helps you to evaluate the static load carrying capacity of a bearing. It is based on the following three assumptions. The first one is that the races are rigid and they retain their circular shape. I hope you remember when I talked about the terminology, this is what you call as the outer race of the bearing, and this is what you call as the inner race of the bearings. So the assumption is that the races are rigid and they retain their circular shape. So when I say the term rigid, it simply means that there will be no deformation in the races. The second assumption is that the balls are equally spaced, and the third assumption is that the balls in the upper half do not support any load. I'll explain the second and third assumption with the help of a diagram on the next slide. So if you look at this diagram, this circle represents the inner race of the bearing, which will be revolving along with the shaft at the shaft rotational speed. These are the rolling elements, basically, or the balls of the bearing. C0 is the static load that we need to evaluate. Now you can see that the angle subtended between the balls is beta, between any two balls, because we made the assumption that the balls are equally spaced. Now you can have a look. There will be balls in the entire circular region, but we are just depicting balls in the lower half. So this is what you call as the lower half of the bearing, and this is what you call as the upper half of the bearing. Now the balls in the lower half will be in contact with the outer race and the inner race, as can be seen here. I've not depicted the outer race, but they will be in contact with the outer race as well. But due to gravity effects and this static load acting here, the balls in the upper half will just be in contact with the inner race, and there will be a little bit clearance between the balls and the outer race. So for that reason, the balls in the upper half do not support any load. So I hope you're clear with all the three assumptions. So now we can have a look at this figure again. which shows the forces acting on the inner race through the rolling elements, which supports the static load C naught. Now it is assumed that there is a single row of bearings. Now, considering the equilibrium of forces in the vertical direction, it is easy to write this equation. So this equation is basically, if we talk about the resolution of forces in the vertical direction, that C naught will be equal to P1 plus P2 cos beta plus P2 cos beta plus P3 cos 2 beta plus P3 cos 2 beta. So we get this equation. Now, as the races are rigid, only balls are deformed. This was our first assumption. Now, suppose that delta 1 is the deformation at the most heavily stressed ball, which is ball number 1, this ball. And this is the delta 1 deformation that occurred due to this ball. Now, due to this deformation, the inner race is deflected with respect to the outer race through delta 1. So therefore, the center of the inner ring, which was earlier O, shifts to O dash through the distance delta 1 without changing its shape. So the inner race is, because it's assumed to be rigid, it still retains the circular form, but it deflects by a distance delta 1 from its earlier position. Now, let's have a look at this equation. That is delta 2 equal to delta 1 cos beta. Delta 2 is the radial deflection for this particular ball. And it's easy to write delta 2 equal to delta 1 cos beta by resolution of these radial distances. Or delta 2 by delta 1 equal to cos beta. Now there's this equation which is known as the Hertz equation, which is specifically used in the case of bearings. And it provides a relationship between the load and the deflection at each ball, which is equal to delta is proportional to P raised to power 2 by 3. So therefore we can write delta 1 equal to C1 into P1 raised to power 2 by 3 and delta 2 equal to C1 into P2 raised to power 2 by 3. This C1 in these two equations is basically a constant of proportionality. Just be careful that the C naught that we look at here is the static load carrying capacity that we are trying to evaluate, and these C1s are just proportionality constants. Please do not confuse them with each other. So delta 2 by delta 1 can be written as P2 by P1 raised to power 2 by 3, and P2 by P1 raised to power 2 by 3 is equal to cos beta, because delta 2 by delta 1 is equal to cos beta, which we derived earlier. So finally P2 is equal to P1 cos beta raised to power 3 by 2, and in a similar way we can also say P3 is equal to P1 into cos 2 beta raised to power 3 by 2. So you can see that we have transformed P2 and P1 in terms of P1 and just cos beta in both these equations. So going back to our original equation, which is C naught equal to P1 plus 2P2 cos beta plus 2P3 cos 2 beta, we will replace P2 and P3 from the last slide in this equation. As and when we do that, we can see that we can take P1 as a common term and rewrite this equation in this term. So we can write the above equation as C naught equal to P1 into M, where M is written as this term. Now just have a careful look that M is represented just in terms of beta term. Alright, so beta can be written as 360 by Z, where Z is the number of balls. And how are we able to write this equation? Because we have assumed that the balls are equidistant. So just have a look at this table now. So if we know the number of balls in a particular bearing, we can easily evaluate M, because M involves a simple beta, M involves a beta term, and beta can be evaluated from Z from this equation. So we have Z, so we have values for M. We can evaluate a parameter which is Z by M, that is coming out to be, that is coming out here. So just have a careful look that these terms are very much consistent. They are in close vicinity of one another. So Strybach suggested that the value for Z by M should be equal to 5. So replacing the Z by M term in C naught equal to P1 by M, and we can write it as C naught equal to 1 by 5 ZP1. Now from experimental evidence, it is found that the force P1 required to produce a given permanent deformation of the ball can be written as P1 equal to KD square, where D is the ball diameter and the factor K depends upon the radii of curvature at the point of contact and on the moduli of elasticity of materials. So C naught can be finally written as K into D square into Z divided by 5, and the above equation is known as the Strybak's equation. Now, with all these concepts in mind, let's move to the second topic, that is the dynamic load carrying capacity of a bearing. Now, the formal definition, I hope from the previous slides you remember when I say dynamic, dynamic means that the machine is still in operation, is in operation actually. Static means that the machine was not in operation. So the dynamic load capacity is based on empirical testing in which a load that is constant in magnitude and normal to the load bearing surface allows the bearing to achieve number of revolutions without fatigue failure. So in simple terms, it means that if you have a bearing testing machine, you will install bearings on that machine, apply a predefined constant load and run the machine at a particular RPM. So over a period of time or after a certain number of revolutions, due to wear and tear and fatigue, the bearing will fail. So the point at which the bearing fails, or after the number of hours after which a bearing fails, or the number of revolutions after a bearing after which a bearing fails, is what you call as the life of a bearing. So for example, you can say that the life of the bearing is 1000 hours at this particular predefined constant load and RPM, or you can say that the life of the bearing is 1 million revolutions at this predefined constant load and RPM. So the life of an individual ball bearing is defined as the number of revolutions or hours of service at some given constant speed which the bearing runs before the first evidence of fatigue crack in balls or races. Now, since the life of a single bearing is difficult to predict, it is necessary to define the life in terms of a statistical average performance for a group of bearings. Now, bearings are rated, so based on this idea, the bearings are rated on one of the two criteria. First, either the average life of a group of bearings or the life which 90% of the bearings will reach or exceed. So the second criteria is widely used in bearing industry. So based on the second criteria, we have a new term which is rating life. Now the rating life of a group of apparently identical ball bearings is defined as the number of revolutions that 90% of the bearings will complete or exceed before the first evidence of fatigue crack. Now there are a number of terms used for this rating life. It is called as minimum life, catalog life, L10 life, B10 life. And in the next session as well, or in the next slides as well, we will use the term L10 life. Now note that the life of an individual ball bearing may be different from the rating life, but for majority of the bearings, the actual life is considerably more than the rated life. So finally, the dynamic load carrying capacity of a bearing is defined as the radial load in radial bearings or thrust load in thrust bearings that can be carried for a minimum life of 1 million revolutions. Now, just as in the case of static load carrying capacity, the dynamic load carrying capacity is also available in the manufacturer's catalog for a particular type of bearing. But bearings. Now coming to a new concept, that is the equivalent bearing load. Now you must understand that in actual applications, the force acting on the bearing has two components, as we discussed earlier, that is the radial component and the thrust or the axial component. Now it is therefore necessary to convert the two components acting on the bearing into a single hypothetical load, fulfilling the conditions applied to the dynamic load carrying capacity. Then the hypothetical load can be compared with the dynamic load capacity. So this equivalent dynamic load is defined as the constant radial load in radial bearings or thrust load in thrust bearings, which if applied to bearings would give the same life as that which the bearing will attain under actual condition of forces. So the expression for equivalent dynamic load can be written as P equal to X into V into Fr plus Y into Fa, where P is equal to equivalent dynamic load in newtons, Fr is equal to radial load in newtons, Fa is axial or thrust load in newtons, V is the race rotation factor. At X and Y are radial and thrust factors respectively, and their values are given in the manufacturer's catalog. Now, one important thing that needs to be understood is that the value of V is 1 when the inner race rotates while the outer race is held stationary in the housing. And secondly, the value of V is 1.2 when the outer race rotates with respect to load while the inner race remains stationary. Also, another important point, when the bearing is simply subjected to a pure radial load, this equation here will simply reduce to P is equal to Fr. And when the bearing is subjected to pure thrust load, this equation here is simply reduced to P equal to Fa. Now we move to the final concept, that is the load-life relationship. Now the relationship between the dynamic load carrying capacity, the equivalent dynamic load and the bearing life is given by L10 equal to C by P raised to power small p, where L10 is the rated bearing life in million revolutions, C is the dynamic load capacity in newtons, small p is 3 for ball bearings, and small p is equal to 10 by 3 for roller bearings. The relationship between life in million revolutions and life in working hours is given by L10 equal to 60 N L10H divided by 10 raised to power 6, where L10H is the rated bearing life in hours and N is equal to speed of rotation in RPM. So I'm going to end this session right here. So this is where I have covered all the theoretical aspects related to the design of bearings. If you have any doubts or concerns, please feel free to email me or get in touch with me. I'll be happy to help. In the next session, I'll be I'll be going through some of the numericals and some more fundamental